welcome everyone. We will start today the second day of the School of Electrochemistry, and it's a great pleasure to have all of you here today. And yesterday we received a lot of views in the YouTube. Thank you very much. We have around 200 views during the presentations. And today we hope that we have the same attendance in the YouTube and here in the Zoom meeting room. Today we'll have a notable lectures and until to start, Victor has a pending question to answer from yesterday, and he will try to answer the question from Andrea, if I am not wrong. And Victor, if you would like to discuss the question.
Can you see my screen?
Yes.
Okay, good morning, everyone. So the question yesterday was regarding this diagram on the left here, and was regarding what is the redox equilibrium potential if we have this energy levels, different energy levels for oxidation reduction, right? So this diagram on the left is a simplification of this one on the right. And what we have actually is a distribution of states, so of energy states, right? So you have different energy states for the oxidized and the reduced species because of because they have different charge and also a different solvation around these ions. Okay, so just to remember that the Fermi energy of the electrode is the electrochemical potential that we are changing or controlling, right? And when we have equilibrium, the Fermi energy of the electrode will be here in the redox potential. And then when we move this Fermi energy of the electrode, then we can have the oxidation or the reduction of the species. So I think that answer the question from yesterday, right?
Yes,
and
perfect.
If there is anything else, then we'll talk on Friday again, so we can discuss more if you need it. All right, thank you for your time.
Thank you, Victor, to come here to answer the question. And
no worries, thank you.
Thank you very much. And if the question is pending yet, Andrea could do the question on Friday. And
yes.
Now let's start our lecture from today. It's a great pleasure to have here Professor Susana, and Susana will discuss with us the first lecture about electrokinetics, and I will let me introduce Susana. It's a great pleasure to have Susana here. Susana, born in Cordoba, Argentina, and she got the degree of Bachelor in Physical Chemistry in the National University of Cordoba, Argentina, and her PhD in the chemistry in the same institution. In the period from 1989 to 1990, during her postdoc, she worked at University Paris at Marie Curie in Paris, in France. At the end of 19th, she moved to Brazil as visiting research at the Physics Institute at Campinas University, Unicamp, and the Chemistry Department of São Carlos Federal University. In 1996, she was hired as assistant professor at the Institute of Chemistry, University of São Paulo, and since 2006, she is full professor at the same institute. Here, where she has also involved in different executive duties. Her main research lines are the electrochemical study of nanomaterials and the relationship between size, geometry, reactivity of inorganic and organic materials, and composites. At all, she published around 200 papers in peer-reviewed journal in the high score of citation. Additionally, she is a member of the editorial board of the Journal of Electroanalytical Chemistry and editor-in-chief of Química Nova, and publication of Brazilian Chemical Society. Her works have been repeatedly awarded by the Electrochemistry and Chemistry of Material Division of Brazilian Chemical Society, and in 2000, In 2008, President Luiz Inácio Lula da Silva gave her the National Order of Scientific Merit. She is also full member of the Brazilian Academy of Science and the São Paulo State Academy of Science. The International Society of Electrochemistry awarded her with the Tajima Prize for Young Authors in 2000, and she has also been elected as Vice President of the Society. With this, it's a great pleasure to have you here, Susana, today to talk with us about electrokinetics, and the stage is yours. We could share your screen, and thank you very much to be here. It's a pleasure for us to listen to you today.
Okay, thank you, Tiago, for the presentation. I am going to share my screen. Hope that everything is fine.
Yes.
Okay.
Perfect.
I'm going to pick the laser. Okay, so good morning, everybody. I am going to continue with the talk that Victor has given to you yesterday, and we are continuing to speak about electrochemical kinetics. So we are going to speak about this reaction, or the kinetic of this reaction, that it seems simple, like it is written here, but you know that it is not simple at all, because we have the transverse charge from the electron to the oxidized species of the reduced species that they are in solution, and we have many paths, and we have to determine in the whole reaction which of those paths are more important, or are determining for the kinetic of the electron. The other thing is that when we speak about electrons, we have a lot of materials that can be electrons, you know, metals, carbon, oxide, covered metals, semiconductors, conducting metal, conducting polymers, modify electrons, and so on. And when we speak in electrolytes, it is also a wide word. So we have aqueous solution, non-aqueous solution, polyelectrolytes, ionic liquids, for example, molten salts, ionic conductors, solid conductors. Okay, so if you are going to speak about electrochemical kinetics, we have to start with the point of the equilibrium that you were speaking about with Victor. So we know that the equilibrium is dynamic, and taking the kinetic definition of equilibrium for this reaction, so we can write the reaction with these arrows, and you know that you have a kinetic constant for the forward reaction and a kinetic constant for the back reaction. At equilibrium, obviously, the rate of the forward reaction is equal to the rate to the background reaction. So it is to say that, as we know from chemical kinetics, the rate that is equal to the constant rate for the forward reaction times the concentration of O, that it is a reaction, at the surface of the electron, it is equal to the rate in the other sense. So you have also the kinetic constant and the concentration of the reactant, that it is R. That happens when the potential it is equal to the equilibrium potential. That is to say, when we have the over potential equal to zero. At that point, this implies that the current, that it is the measure of the electrochemical kinetics of the electrochemical rate, the current in one sense, or the positive sense or the negative sense, are equal. So the net current density at the equilibrium potential is zero. Well, but the other thing is that we know that in this case, that we have an electrochemical reaction, the rate constant are dependent on the potential. So changing the potential will perturb the equilibrium at the interface. The other thing is that we have to distinguish here is that we can speak about the potential at equilibrium or the formal potential at the equilibrium. Only at the formal potential, that is to say that it is denoted like this, the rate constant for the forward and the backward reactions are equal. So at that point, when we can use the formal potential, we have this. At the equilibrium, the rates are equal. That's to say that we have this. So at the equilibrium, we have the negative current and the positive current. That is to say, the background, the forward current and the backward current are equal to that which is called the exchange current density, but the net current that passes is zero. But we are going to speak a lot more about this. What happens when we have the formal potential and both rate constants are equal, and this can be equal, or it is denoted as the standard rate constant. So what is this kind of dependence of the rate constant? Okay, so we are going to have that the rate constant, it is equal to that K's, and we have a term that is dependent on the potential for the forward reaction and the backward reaction. And when we have this exponential term, we have this alpha, or in the other sense, the 1 minus alpha, which is called the transfer coefficient. We are going to speak more about the transfer coefficient later. So what are we talking about this? We have here a plot of the values of the rate constant as a function of the potential. And we can see that the reduction rate constant, that is the forward reaction, supposing that we have a standard rate constant of 0.001, and we suppose that the transfer coefficient it is equal to half, and we suppose 1 electron. We have this kind of dependence for the forward rate constant, and this kind of dependence for the background discussion, the reduction and the oxidation. And obviously, you can see that for negative potentials or negative overpotentials, because here we have the overpotential, for negative overpotentials, the forward reaction of the forward rate constant, it is higher. So the speed is higher. And we have exactly the same, but for the oxidation, but when we have positive overpotentials. How can we explain this change in the value of the rate constant with change in the potential? Okay, we start by recalling why this depends. We start by recalling this equation, the dependence of, or the equality for the electrochemical potential for O, for R, and for the electron. We know that O is in solution, R is also in solution, and obviously the electron is in the metal. But we know that the relative values depend on the potential across the interface. So delta phi, the potential that we are changing. So we are saying that this is controlled by the electron potential. And all this is regarding with this kind of plots that obviously you know, energy as the function of the reaction coordinate, and the electron potential will affect the free energies of the activation or the transition state that we have here, and obviously also the overall free energy change. So if we denote with this double star the transition state, so here, so if we have our reaction O minus N electrodes that gives R, so this is the energy well for the forward reaction, and this is the energy well for the background reaction. And here, at the point of crossing, we have exactly the transition state. Obviously, you can see here, this is the value for the change in free energy for the forward reaction, and this is the value for the change in free energy for the transition state in the background reaction. And this difference will be the free energy change of the reaction. How is the form of this plot in the case that we have the equilibrium? In the case that we have the equilibrium, we have that particular case where both the change in free energy of the transition state for one side and for the other are equal. So we have that the change in free energy at equilibrium, we know that it is equal to 0. That is the case that we have exactly at equilibrium. And we can perturb that equilibrium by changing the potential. Why? Because it is an electrochemical reaction, and we know that these transition states, the forward and the backward, will change with the potential. So we are going to do this now. We are going to take the reaction from the equilibrium. We are going to provoke the path of current. And this is what we have. In the case of the reduction, so we have this sense of the reaction that is the main flux. So in the case of the reaction, we are going to put the electrode at a potential, the potential electrode less than the formal equilibrium potential. We have this kind. So we have in this case that the change in the free energy of transition for the forward reaction is less than the change in the free energy transition for the background reaction. When we provoke the oxidation, so we put a potential that it is higher than the former equilibrium potential, we have this situation. So we have this situation. So in this case, it is obvious that this sense of the reaction is the spontaneous. And in this case, we are going to have exactly the contrary that in this case. But we are also seeing that the minimum energy change by NF E minus E formal, the geometry of the energy value is affected by the potential. So the energy value affects the transition state, and how this change will be managed by this value alpha. Because we are not going to have exactly this. We are going to have that in this case, the well will be modified, and the well will be more modified each time that we change the potential. So the meaning of this transfer coefficient, alpha, describe how sensitive the transition state is to changes in the driving force of the reaction. So if we put a plot, for example, of the free energy as the function of the reaction coordinate, so we have these kind of curves, but we do this as a function of the electron potential. When we put more potential, or we put a potential that is more far away from the equilibrium, we are going to distort this well. So alpha reflects how this change in the free energy of transition depends on the potential. It is regarded with this slope, the slope of the change in the free energy of transition versus the potential. And it is about the half of O and R. So normally, for most reactions, we can consider that alpha is equal to half or 0.5. But typically, depending on the reaction, we can have, it can vary from 0.2 to 0.8. And obviously, the maximum value will be 1 and the minus value will be 0. But we are going to speak a more about the activated complex in electrochemical kinetics. So taking a common expression from the activated complex from the iron theory, we have this. We have that the rate constant will depend on different factors, and we have here an exponential factor where we have the change in the free energy of transition. And substituting this value by the potential dependence that we know that in this case it is important, we know that the delta G of transition will be equal to the delta G of transition at the equilibrium plus the potential with the term with the potential dependent. So in this case, we are going to get this equation, and in this equation we can distinguish two parts: a part that it is independent of the potential, and a part, or an exponential, that it is dependent of the potential. So this part that it is independent of the potential is what it is called the standard rate constant that we have defined in the first part of the talk, the K is. So now we know that this standard rate constant depends on all the things. Depends on all the things, and all the things depends on what? What? Obviously, that we have a molecular origin of this standard rate constant. See? Because the electron transfer requires exchange of charge and simultaneous reorganization of ligand of solvents. Even that it is very fast, normally it is very fast. So outer sphere electron transfer does not involve ligand coordination change, because we have this kind of reaction. But if we change the charge of the ion, that it is what happened in an electrochemical reaction, because we are changing the charge. Changing the charge of the ion alters the M-ligand bond length and reposition of solvent molecules within solvation sphere. And we know that here we have steps that happen in very, very different rates. We have the electron transfer by one way, that it is very, very fast, and the solvent reorganization, that it is very slow compared with the electron transfer. So coming back to the activated complex theory that we were speaking before, what are all these terms? We have K transition that describes the pre-equilibrium at the electrode surface. So the ratio of reactant reaction in reactive position on the electrode to that in the bulk. So on the bulk we have a ratio, but at the moment of the reaction we can have another ratio different from the bulk. Here, Nies describes frequency of ligand or solvent reorganization that we know that it is very, very small, the molecular motion that takes system to the transition state. And finally, we have this term that it is the electronic transmission coefficient that reflects the tunneling of the electron at the transition state. And this term, it is dependent on the distance from the electrode to the redox center. And obviously, this is very important. And we have a dependent with the geometry and the kind of the redox center or the molecule that we are trying to reduce or oxidize. This is very dramatic, and it was very emphasized, for example, in the case of biomolecules. In the case of biomolecules, you have an redox centers that can be depending on the organization of that biomolecule regarding the electron. This redox center can be very close, for example, as in this case, that the distance from the redox center to the electrode is denoted as 5 angstrom, or can be, for example, is the redox or the biomolecules is like this and the redox center it at 12 angstrom. You can see that we have in K a very different value, and we can have this situation where the redox center is very far from the electron, obviously reflecting in the Chi-L. It is very much difficult for the electron to do the tunneling in this case than in this case. And this can provoke changes enormous in the rate constant. In these three situations, only for showing to you, we can have changes of 10 to 10 in the rate constant. So we are going to see that finally the change in the free energy of transition depends on the molecular structure. So high reorganization energy that we are going to call lambda implies in large changes in free energy, so slow kinetics. This is, for example, the case of this kind of ion. In the case, for example, of the anthracene anion radical, we have the case that we have a low reorganization energy, so it gives small delta G, hence fast kinetics. Only for showing you, we have, for example, experimental values of the standard rate constant for different oxidized species, and they are very common in electrochemical, for example, anthracene, ferritinite, permanganate, and we have here these other that we are talking about. So we can see that the changes in the value of the delta G, it is not so important, or it seems that it is not so important, but it leads at very, very different changes in the standard rate constant. Okay, by coming back to the heterogeneous rate constant, so we have speak about the standard rate constant, but it is a part of the rate constant. So we have this part that it is dependent of the potential. And when we combine this, from these values, we can derive the Battle-Bolmer reaction or equation that I know that Victor has already introduced. So this is the fundamental equation of electrochemical because it relates the current with the potential, or the current with the over potential. It appears also the transfer, the transfer coefficient, and also we have here a very important parameter that is the exchange current. So if we do a plot of the current as a function of the over potential, the red line, it is the representation of the Battle-Bolmer equation, and in blue or in red, what we have, they are the simulations for the oxidation or the reduction current. And we can see that obviously at over potential equal to 0, we know that the liquid current density is 0. So we have this point here, and this value and this value are the corresponding exchange current density of oxidation and reduction. So summarizing this part, so we have a representation of a polarization curve, current as a function of the potential. When we have the reduction, we are going to have the forward reaction that it is facilitated. We have this type of energy curves, and we have a negative current. At equilibrium, we have 0 current or 0 speed. And when we have the oxidation, we have current potential, current density that is positive, and we are going to have this kind of bar. But if we speak in electrochemical kinetics, obviously, if we try or to improve the electrochemical kinetic of the electron. And for this, we are going to speak in a very, very important part of the electrochemistry, that it is electrocatalysis. Electrocatalysis is very important in electrochemistry because, for example, if we speak in power sources, we have the conversion of chemical energy to electrical energy. If we speak in electrolyzers, we have the conversion of electrical energy into chemical energy. What are we speaking about? So we have an electrolyzer, we have our 2 electrodes, we are going to put energy and the reactants, and we are going to obtain the products. In the case of the batteries, we are going to have the conversion of the reactions in products, and from this reaction, we are going to obtain energy. In the case of the fuel cells, they are all electrochemical devices that you know very well. You are going to put the reagent for obtaining the product. We are going to obtain the product, and also we are going to obtain energy. And for all this, we have to obtain the optimization of this electrochemical process, always. So all the things that we were speaking about, the electrochemical kinetics, the electrochemical kinetics must be improved in electrocatalysis. This is most of the things that all electrochemicals are searching. And the NE in this reaction is the amount of electricity. And this amount of electricity we can consider as an additional specific reaction. So this electrical energy, in the case of power sources, we know that we search for production. For in the case of electrolyzers, we have a consumption of the electrical energy, but which is the aim of these devices? In the case of power sources, we search for obtaining the maximum current with maximum voltage, delta V. In the case of electrolyzers, we search for the maximum current, but utilizing the minimum delta V. So in both cases, maximum current means maximum rate with maximum delta V, but in the case of the electrolyzer, maximum rate with the minimum delta V. Okay, so, but this delta V is the change in potential plus or minus over potentials. And these over potentials are the energy dissipation to overcome reaction resistance. These reaction resistance are many of them. For example, the components of delta V are the change in potentials, a summatory of over potentials that we are going to speak about this, a term that it is an ohmic drop, and a term that we are going to put T because we have this problem to overcome that, for example, in the case of electrolyzers or in the case of power sources, at very, very long time of operations. We are going to speak about each of these terms, what they mean, and how can we overcome these problems. So the first term, the term delta E, the meaning is the thermodynamic potential difference. So how can we modify the term? It can only be modified by modifying the nature of the electro process. So if we are studying a special electro process, for example, chlorine hydrogen cell, okay, we are going to have this delta E that it can be modified. Or the chlorine oxygen cell, we are going to have this delta E that it cannot be modified. Instead that we change the nature of the electron. The IR term, the meaning is the ohmic drop in the electrons and in the solution between the electrons. This is an experimental problem that can be overcome. The strategy is to increase the conductivity of the electron materials, decrease the inter-electron distance, so to change the geometry of your electrochemical cell, but sometimes depending on the device or depending the type of the experiments that you are doing, it cannot be done. Another thing that it is very important, for example, in the case of the gas evolution reactions, is to avoid the formation of bubbles that curtains the electrons. So these are the strategies that I can use to diminish the IR term. The overpotential term, the meaning is the sum of anodic and cathodic of the potential. And the strategy to diminish this or increasing this overpotential is to search for materials with low values of overpotential, to search for good electrocatalyzers. And finally, the delta V term that almost anybody talk about, the meaning is that it is directly related with instability. And this term increases with time and of the delta V applied to the reactor. So the meaning of this term is directly related with stability of your device, stability of your battery or stability of your electrolyzer. And you know that there is always a compromise between stability and activity. And this is a thing that we have to overcome, because the strategy is to search for stable materials, but normally stable materials, normally they are not the most active. So we have always a compromise.
Susana,
So,
1 second.
See, yes.
We have a question here in the chat, and there is one of the person here is talking about if it's possible to you to talk a little bit more what is overpotential.
The overpotential.
Yeah.
And so the overpotential, we are going to come back here. If we have here the fundamental equation of the electrochemistry, Battle-Polymer equation. So we have the current and we have here the potential. When you have the potential that you are applying minus the formal equilibrium potential. This difference between the potential that you are applying and the formal equilibrium potential, this is the overpotential. So it is the potential that it is different, which is the difference between the potential in equilibrium and the potential that you have applied to take out your reaction from the equilibrium. If you are at the equilibrium potential, the current or the rate of the electrochemical reaction is 0. You are only, so you are in this situation, 0 over potential, 0 over potential, 0 current. When you change the potential, so you are applying negative over potentials or positive over potential, you are going to observe a passage of current. Positive current in the case that the overpotentials are positive. So the potential that you are applying is higher than the formal equilibrium potential, or negative current when you apply a potential that is more negative than the equilibrium formal potential. Is it right?
Yes, I think. Oh, there is one here. Hona requested another. If it's possible to you to discuss, we have a lot of questions now. I need to change a little bit. The first one is, could you explain how formal potential is obtained or calculated?
The formal potential is thermodynamic. The formal potential is thermodynamic. Is the potential that you have at Nernst equation. Nernst is when you have equilibrium. So and if at equilibrium you are going to have 0 current or net current obtained. That is why when you speak about overpotential in some books, you are going to have the expression that the overpotential is the potential that provokes the passage of current. So it is the potential that you have to apply to see a current, positive or negative, depending if you are oxidizing or you are reducing.
Perfect. I think this question answered the pose question here. How can we have the precise value? The precise value is related when we have current passing to the cell. And the other one is about Rona is talk if it's possible to you to discuss the difference between, it's the same. It's the difference between the formal potential and the equilibrium potential. And the last one is Abdul is talking about if it's I was wondering what is the difference between over potential and zeta potential. There is a confusion here,
no. The zeta potential is the potential of charge that you have at the surface of the electrode. and it depends on the surface that you have. The overall potential, it is related with the potential that you apply to do your experiment, to oxidize or to reduce. Is it right?
Yeah, perfect. No more question, and all the questions was replied, and everyone is saying thank you for the answers. Thank you, Susana.
Okay. So coming back here, so we are going to speak now about heterogeneous catalysis, because at the electrode we have an heterogeneous catalysis that we have to deal with. So general, we can consider that electrocatalysis is the variation of the electron reaction rate at constant potential. But specifically, which is important, is the effect of the electron material on the electron reaction rate. Normally, when you use electrochemistry, you prepare an electrode, etc., for a specific reaction for using as a sensor or an electrolyzer or the battery. So specifically, we are going to study the effect of the electron material on the electron reaction rate. So when we search for new materials or new operating conditions in electrocatalysis, we want to improve the activity, the efficiency, the selectivity. All these kind of things are important. We want to reduce the investment costs or operational costs. We want to increase lifetime because we need stable conditions, and we want to avoid pollution. All these kind of things are important, and we are looking for when we do electrocatalysis. And we have to consider electronic factors, primary and secondary factors. The primary factors are the chemical interaction between electrosurface and reactants, intermediates or products. And the secondary are the non-specific interaction between the electron surface reactant, intermediate of products. For example, other reactions that we can have after that the electron transfer produced. When we speak about the primary effects, we have to introduce one of the most important plots that we have in electrocatalysis, that they are what we call the volcano plots. Which are these volcano plots that you are going to, in practically most papers in electrocatalysis, you have, for example, sometimes a volcano plot. It's a plot that defines the catalytic activity of, for example, a metal for a specific reaction as a function of the bond strength of the absorbate. So when we have a very strong bond strength between, for example, the surface of your electrode and the absorbate, you are going to have a deabsorption limited. When you are going to have a weak bond strength between the electrode surface and your absorbate, the absorption is limited, so it is very difficult for that absorbate to interact with the surface. In this case, the catalytic activity will be very low, and you are going to have an optimal binding when you have a compromise between the catalytic activity and its bond strength. When we speak about this in electrochemistry, what are we talking about? Okay, so the electrocatalytic activity is the current, the rate of the reaction, and the absorption energy of the delta G of the absorption for, I don't know, hydrogen, for example, for the hydrogen evolution. So when you are going to have a a degree of cover that it is approximately 0, or if you have a degree of cover that approximately 1, you are going to be in one of this point or the other. And when you have exactly the compromise or the optimized situation, is that you are going to have the electrocatalytic activity that it is higher. So this is, for example, a volcano plot for the hydrogen evolution on metal electrodes. So here at these points, you have, for example, lead, cadmium, thallium, indium. At these, you have other bulk metals, titanium, tantalum, niobium. These both are not good catalysts for hydrogen evolution. Where you have the most active metal for hydrogen evolution reaction at the point of the volcano. Where what do you have here? Okay, platinum, rhodium, iridium, all the noble metals. You have also, for example, gold, but you can see that gold is less active than platinum.
Susana, we have a question.
Yes.
Sorry
yes.
to interrupt you. It's about when it was mentioned about the degree of coverage. One of the questions about how we can measure the degree of coverage.
Well, to measure the degree of cover, there are. It depends on the reaction, and it depends also. There are different methods. In this case, we are still talking about that when we have almost no interaction with your surface, you are in this situation when you have a lot of interaction. So they are a lot of absorbate on your site electrode. You are in this case, but to measure this kind of interaction in electrochemistry, there is always indirect situations. You can do it by potential. For example, it is related with the potential of zero charge that you were asking before. But these are other kind of measurements not related directly with electrocatalysis.
Perfect, thank you.
Okay, so speaking more about electrocatalysis.
Oh, sorry, Susana, to interrupt you again. There is a question about the volcano plot. If it's possible to obtain the volcano plot for oxide material, such as oxide titanium and oxide zinc, and semiconductors.
Okay, yes, and it depends on the reaction also. You can do also a volcano plot, for example, for one material, but for at different situations. Also, it's a volcano plot.
Perfect.
For example, platinum, but platinum at different crystallographic orientations. Yes.
Thank you very much, Susana.
Okay, so when we speak about electrocatalysts, and you know that, okay, we are searching for the maximum current at the minimum, for example, potential. Suppose that we are trying to search for the maximum electrocatalytic activity, and we have two kinds of electrocatalysts, electrocatalyst 1 and electrocatalyst 2. And we want to compare this electrocatalyst, which is the best electrocatalyst. Okay, if I have a polarization curve, for example, current as a function of potential for both electrocatalysts, by looking at this plot, I would say, okay, I think that the electrocatalyst 1 is much better than electrocatalyst 2. Why? Because, for example, at this potential, at the same potential, evidently, the current in 1 is much higher than in carbon in 2. But this is, the plot is not complete. If I see this, we can do different assessment. For example, we are continue to discuss about electrocatalyst 1 and electrocatalyst 2. If I now do a plot of the type of the Tafel plot, for example, a logarithm of the current as a function of potential, I can have this situation for these two electrocatalysts that I am comparing, or I can have this situation, or I can have this situation. So, for example, in this case, evidently that, for example, for low potentials, electrocatalyst 1 is much better than electrocatalyst 2 because the current that we are obtaining at low potential is higher. But at high potential, 2 is much better than 1. In this case, for example, we have that the Tafel slopes are exactly equal. By when we are going to see the exchange current density, that is to say the exchange current, the current density when we are going to go to the zero potential, they are different. We have also this case where we have, for example, at low potentials that we have a situation that is similar to this, and at high potential we have a situation that is completely different. At high potential we can see that 2 is much better than electrocatalyst 1. So the relative assessment of activity, you cannot do only with one point. We have to have a whole picture of the situation. So we are going to compare electronic and geometric factors. In the case of electronic factors, structure and chemical composition of the material. Geometric factors, they are only related to surface area of the material or the morphology of the material. In the case as, for example, we are comparing here the curves for nickel, smooth nickel or porous nickel. You can see that here, you can see, okay, this material is much active. It is only an effect of area. So we have intensive quantities independent of surface area extension and extensive quantities that they are dependent of surface area extension. In intensive quantities, for example, we are going we have to relate to the Tafel slope and the point of zero charge. These things do not depend on theoretically, they are not depend on the area of the electron. So, for example, the Tafel slope is related to the reaction mechanism. So if we have a change in the Tafel slope, it means that we have changed the mechanism, and it can happen, for example, by changing the potential if you are at very low potential or a very high potential. And the point of zero charge, it is related with surface chemistry. So we can see here, for example, the change in the Tafel slope for smooth nickel and sandblasted nickel. In this case, the Tafel slope are equal, so we have no change in the mechanism. But when we change the chemistry of the material, because we have no here nickels, we have a nickel raney alloy, we can see that the mechanism is different. The Tafel slope has changed. We have also, for example, the effect of the surface crystallographic orientation. We have not a change in the Tafel law, but we have a change in activity. Very, very important. Evidently, that we have different activity for the different crystallographic orientations. For example, in the case of silver. The effect of size in the particle size. This value here is the value of the Tafel slope. We have here, for example, the case of ruthenium oxide for oxygen evolution. Ruthenium oxide is the best electrocatalyst for oxygen evolution. And you can see that from when the particle size is from 10 to approximately 500, we have not changed in the Tafel law. And we have this here, a Tafel law very, very low. But when we have other particle size, for example, we enter in very, very small particle size, we can see that the mechanism has changed completely. The Tafel laws go from 30 to approximately 60. Also, the effect of the preparation of the electrostatic chain. Also for oxygen evolution, we have a mixture of ruthenium oxide with iridium oxide. So we can see here how the Tafel law changed with the composition, obviously. Instead that we are putting more iridium oxide, we are having a change in the Tafel law. But this is completely different if for the same composition we prepare by aqueous mixture, for non-aqueous mixture, or by reactor sputtering. So we can see here how it is sensitive for for this kind of electrodes. Here you have, for example, also for the composition for chlorine evolution or for hydrogen evolution. So the general trend.
Sorry, Susana.
Yes.
Sorry to interrupt you again. We have a question here from Marian and how we can understand the effects of the phases. Is DFT calculations is the only option to look in that?
Very good question, and I would say that DFT would be the only answer. The only answer, the only way to because you can do many experiments, but to understand this, the mechanism, you have to go to DFT calculations and also to spectroelectrochemical measurements. But not all the time we can do this kind of measurements.
Thank you, Susana.
Okay, so the general trends in research, we can see that we try to maximize the surface area to obtain better dispersion specific technology and synergic effects, for example, better mixing composite materials. And you know that the electrocatalyst, the material for electrode, depending on the kind of reaction, I have put here some of the reactions that we have, but now, for example, oxygen evolution, oxygen reduction, chlorine evolution, CO2 reduction, nitrogen reduction, the variety of electrocatalysts that we have, they are enormous. And also, what happened, for example, now for the impact of control materials for electrocatalytic applications. When we speak about control material, we speak not only in changing the properties or the composition or the structure or the size and shape, but in a way that must be controlled. And for this, we need to control the synthesis of this material. So when we speak about this, we have the effect of size, that it is obvious. So we change the size, we increase the specific surface area, we expose more atoms, so we are going to have more exposed sites. But also, if we are able to control the shape of the catalytic of the materials, we have important electrocatalytic effects. For example, when we speak about by controlling the geometry of the nanoparticles, here is an example for palladium nanoparticles. They have the same size, but they have different forms. And the size, the phase that they are exposed, they goes from 100 when you have a cube to 111 when you have an octahedron. And you can see that the current density for the same reaction are completely different. So the rate is completely different. I have here another example, for example, with oxides, but in a control form, a copper oxide nanostructure, and you can use also this structure for enzyme-free glucose determination. We are able to prepare these structures. They are the same size, but in different forms, cubes or spheres or octahedra. So you have here all the characterization. And obviously, when you have the cubes, we have a 100 structure. When we have the octahedra, we have a 111 structure. And when we have the spheres, we have a mixture of the both situations. What happens when we do electrochemistry with this? Okay, you can see here the voltammograms for the cubes, the spheres of the octahedron. The electrochemical response is completely different. And when we use these structures for sensing glucose, for example, we can see that maintaining the same quantity of copper onto the electrodes, the response is completely different for octahedron and for cubes. Evidently that cubes are more active. But not only that they are more active, but they are also more selective only to glucose, and they are not selective for the octahedron or the spheres. They are not selective. So you can see how the facet that it is exposed is important for the electrochemical reaction. The other thing is that we have speak that the catalysis or the catalytic activity must be seen also as a function of time, because we have a compromise between the stability and the catalytic activity. And here it is clear that the current density, when we have the cube, and in the function of time, in the third day, in the seventh day, in the fourth day, we have a loss of the catalytic activity. And we have a loss of the catalytic activity until reaching approximately when we have the octahedron in the first day. And also, the other thing, when we are losing the activity, we are also losing the selectivity. And obviously that it must be, I am not going to enter in the details here, but it is related with a loss of this structure. We are losing the structure of 100 for passing to 111. And evidently that the electrochemistry feels that. You can see here, for example, for the cubes of the first day and the cubes in the fourth day, but if we store this in vacuum, so we avoid oxygen, and in this case we have not a change in the catalytic activity, and also the selectivity is remain. But I want to speak to you in another way to boost the electrocatalysis, and it is new in electrochemistry, and it is the combination of electrocatalysis with plasmonics. You know that when we speak about nanoparticles, especially metal nanoparticles, we have we can excite the plasmons of these nanoparticles if we illuminate the nanoparticles with the proper wavelength. So in this case, we are generating a pair of electrons and holes, and we have the hot electrons on the surface of the nanoparticles, and these hot electrons, if we are doing electrochemistry, can be optimized the electrocatalysis. That is to say that it can be combined with the current and increase the current because of the presence, for example, is these hot electrons. What are we talking about? For example, we can, for these structures that we were speaking, we can decorate the structures with tiny gold nanoparticles that are plasmonics, and we are going to combine the electrocatalytic properties of the copper oxide with the plasmonic properties of the copper. How can we do this, and which are the advantages of this? Obviously, we can prepare also bimetallic nanoparticles, and in this case, we have wide possibilities for this to prepare different structures. And obviously, we have many parameters as the type of metals that we want to combine, the reducing agent that we are going to use, the caping agent, temperature, the nucleation. And the advantages for this is that if we are lucky to obtain a synergism, to combine, to couple the L pair, or say to couple the plasmonic, chemical stability and thermal stability. But here, for people that are doing electrochemistry, we have to do a very, very important differentiation. Many people do a confusion between photoelectrochemistry and plasmon-enhanced electrochemistry. They are different phenomena. And I am going to explain you. This is, for example, in this figure, in the part E, you have a photoelectrochemical process. In the photoelectrochemical example, the photoanode is always an N-type semiconductor that it is illuminated with solar light, that is with all the spectrum of light. So when the energy exceeds the band gap, photoexciting electrons move from the valence band to the conduction band through the external circuit, the cathode drive the reduction reaction, and holes remaining in the valence band propel the oxidation reaction. In this case, an external bias you can use or you cannot use, because all the thing, it is provoked by the light. When you have the plasmon coupled with electrochemistry, it is different, because the photoanode, it must be a plasmonic metal that it is illuminated by a single wavelength. And this single wavelength of light must match the plasmonic resonance. If this phenomenon it doesn't occur, you are not going to have plasmonic effect. The photoexcited electrons move from the field electronic state to higher energy unfilled state, resulting in an electron distribution with a higher population above the Fermi level. So the holes with sufficient energy promote the oxidation reaction. In this case, an external bias is always applied. So you have an external bias provoking, for example, hydrogen evolution. You are going to illuminate, and you are going to see an increase of current if you add it to the other current. And the other thing is that in this case, the change in current that you can obtain, it can be very, very tiny. So it's more difficult to measure. I'm going to show you rapidly three cases, for example. So these are, for example, These kind of nanoparticles, they are a gold nucleus with a rhodium dendritic shell. So you have here, for example, the characterization. And you can see that we can change the amount of rhodium that you put here. When you have only the gold nanoparticles, you have this extinction spectra with the band of 5 to 2 nanometers. And when we put rhodium, you change the spectrum. So you have a shift of the plasmonic band of the gold, and you are going to observe here also an increase in the extinction because the plasmonic of the rhodium is in the UV region. Okay. How do we measure? We are going to study the hydrogen revolution reactions with this kind of electrode. We prepare an ink with the nanoparticles and carbon, a very, very tiny amount of the nanoparticles, and we are going to do electrochemistry by illuminating with monochromatic laser. Green, we are going to change to another colors, and here you have the results. So here you have the current, potential current curves for hydrogen evolution. Gold, only rhodium. You can see that in this case the dotted curves corresponds to the dark, and the full curves correspond to the illumination with green light. You can see that when we increase the amount of rhodium, we have a very different current when we illuminate, especially for these nanoparticles that we have 60% and 30% of rhodium. You can see that we have a very different current, and here they are more clearly shown. For the dark, currents are here, and when we illuminate with green, you have this changed current. And also, we can calculate the change in the overpotential when it is illuminated or when it is dark for different wavelengths, with the blue, with the green, and with the red. And you can see that for the all nanoparticles, the change in overpotential, it is more important when we illuminate with green. It is rather important when we illuminate on blue, but it is almost negligible when we illuminate with red. And this matches the extinction spectra. We can see that when we illuminate with the green, that it is in this region, we are in the maximum of the plasmonic absorption of these nanoparticles. When we illuminate with 400, we have also an effect. But when we illuminate with red, we are also, when the plasmonic effect, it is losing, and we have no effect. The other thing is that you can ask, okay, but we are illuminated with a laser, so we must have a change in temperature. What happened? Okay, we can measure the temperature there, and you can see that the change in temperature is almost negligible, even with the time when we illuminate with different power of this laser. So it is not an effect of temperature, it's the effect of the plasmonics. We can also do the calculation of the field, and we can see that for these kinds of nanoparticles, the electric field is maximum when we have the 2 metals mixture. Okay, here you have, for example, for showing you the the Tafel plots, and this is the Tafel slope for the different for the nanoparticles at dark and at the different lasers, and you can see that the Tafel lobe does not change. So we have not a change in the mechanism. So we have only a change in the rate of the solution, but not a change in the mechanism. Another example is, for example, is these bimetallic shells that they are supported on silica or onto graphene. And depending that they are supported on, these shells are of silver and gold, and by changing the proportion, obviously, we are changing the extinction spectra. We are also measured with this kind of materials at different wavelengths. And we are going to use those for the determination of hydrogen peroxide. So these are curves that as they use, for example, as a sensor for dark and for the different lasers. And you can see that depending on the composition of the shells, they are more sensitive or not to the wavelength of the laser. And this matches, if we have here the change in sensitivity in the dark and the light. Here you have the extinction spectra for these nanoparticles, and you can see that we have the maximum change of the maximum boost of the electrocatalysis, depending if we are matching the spectra or not. So this is a demonstration that we have plasmonic effect. And the last example is when we have the combination of the two effects, the photoelectrochemical and the plasmonic electrochemical reaction. For this, we have manganese oxide nanowires that they are decorated with gold nanoparticles. So manganese oxide is a semiconductor, and it is different than in the other cases. And we have also now the semiconductor combined with the plasmonic nanoparticles. So we have here the change in the spectra. We can see here that the structure of the manganese oxide does not change when we decorate with gold. So we have the same material. And we also use to determine the peroxide. So we can see here with no illumination and with hydrogen peroxide. And here you can see when we have the manganese oxide or the manganese oxide decorated in dark and in light. You can see here that when we compare the manganese oxide that it is not decorated, and when we illuminate, we have a change in the current because it is a semiconductor. But this change is much more important when we have the manganese oxide decorated with gold. We can see here, for example, the cubes in the function of the hydrogen peroxide concentration, and we can see that it is very important, the change that we have when we illuminate. This is for the manganese oxide and the manganese oxide decorated. And also this change in sensitivity in between light and dark changes with the amount of gold nanoparticles that we put. And we have a maximum of amount of nanoparticles that we can put that correspond to 5%. And after that, we have a diminution because at this region, even that we have more gold, the gold that it is decorating the manganese oxide is not the same size. We have an agglomeration, so we lose the plasmonic properties. Here also you can see, for example, for different lasers, for the green laser and for the laser in the 800, here we are in the region that we have no plasmonic excitation, so the current is much, much less. And here it is important to see that if we change the laser power, we are changing the temperature, obviously. And we can see that the gold decorating material show a characteristic linear relation with between the reaction kinetics and the irradiance, which is related to the photoelectric behavior, to the plasmonic behavior. When we have no the plasmonic material, which is the blue line, we show an exponential relation with the irradiance, typical from photothermal effect, which follow an Arrhenius type temperature dependence. The other thing that we can see here, if we follow the change in temperature during the illumination with different powers, we can see that the manganese oxide decorated with gold have a more efficient conversion of light to charges for the reaction, lowering the increase of temperature relating to the energy release for the combination of excited electron and holes. So, as a general conclusion, the search for new electrocatalysts can be very important and we are always in the search of new electrocatalysts depending on the reaction. We can boost electrocatalysis by light. The synthesis of nanoparticles and the control synthesis is critical for this kind of experiments. We have to characterize all these kind of nanomaterials. It is very important. Spectroscopic techniques, they are very important to propose mechanisms. And also, as you have asked, DFT calculations are very useful for understanding experimental results. Okay, so thank you very much for your attention, and I am open to questions.
Thank you, Susana. We have until the questions. Thank you very much to talk with us about this amazing work and your work in the Institute too. And Luan is performing a question here. What's the best way to normalize the current value? Because I have seen values normalized by area and in some plots, and the other by grams of material. The big question, the question of $1 million here, because
yes,
about the area, how to normalize that.
Yes, this is a very good question. I think, for example, when you are taking in electrocatalysis, normally you have to compare materials and you have to compare the performance of the material. I like to normalize by the electrochemical area, but sometimes it is very difficult to determine the electrochemical area. So it depends on the material that you have. Obviously, there are many methods to determine the electrochemical area, but sometimes you put normalized by the amount of material. For example, in the case of batteries, this is the normal way to do it. This is the normal way, because normally it's a reaction that is not in the surface, it's a reaction that is in the bulk. It depends on the amount of material. But in electrocatalysis, when it is possible, I think that the main thing is to try to find the electrochemical area.
Yeah, and the next question is about that, about how we can measure area. There is a different ways to measure the area, and depends on the material, but
yes.
One of the questions in this direction.
Yes, okay, you can measure also for example, in the case of batteries, normally they measure by physical methods, for example, by BET. It is very normal. But in the case of that you have to determine the electrochemical area, there are different methods that we have no time here to discuss. It can be by copper UPD, that in the case that you have gold, for example, or by voltammetry, like you have a region that you have not Faraday current. It depends on the material. But other thing that, for example, it is important in the case of nanoparticles, I think, is that to determine the real amount of metal that you have. And in this case, you can normalize the amount of metal that you put on your electrode, for example, by ECP or anatomic method.
Perfect. Thank you very much, Susana, for the amazing lecture. And I will request you to stop to share the screen.
Okay.
And
yes.
we will have a break now, a 15 minutes break. And after that, we will have the next speaker, Professor Denuault. And I will waiting for you in 15 minutes. Thank you very much.
I don't know how you how to interrupt. Okay.
Oh yeah.
Okay. Okay.
Thank you, Susana.
Okay. Thank you.
Hello, everyone. We are back, and let's start our second part of this day. And first of all, I would like to thank you very much, Guy, to accept the invitation to be in this project. It's very special to us to have you here virtually, and thank you very much to be here to present with us. This project was very special, and thank you very much to be here. And I will introduce the Professor Guy Denuault first until his lecture. Guy will stay here virtually for 3 consecutive days. And Professor Guy Denuault is an associate professor of electrochemistry. His research focuses on electroanalytical chemistry with particular emphasis on the theory and application of microelectrodes, scanning, electrochemical microscopy, nanostructure microelectrodes, and the modeling of electrochemical process. This is the topic that Guy will talk with us today. He has been organizing the Southampton Electrochemistry Summer School since 1998. This is the famous school of electrochemistry that we have in the world. Guy is one of the pioneers in this project. Guy undertook his undergrad training at Haynes Institute of Technology, where he received his first degree subsequently at Bordeaux University, where he received his master's degree. He joined to the Southampton Electrochemistry Group and carried out experimental and theoretical, analytical plus modeling investigations into the application of ultramicroelectrode in mechanistics and kinetic studies of coupled chemical reaction. He received his PhD in 1989, and he moved to University of Texas at Austin, where in the group of Alan Bard, he worked on the development of scanning electrochemical microscopy. Additionally, he returned to Southampton and he was awarded 5 years in Advanced Research Fellow. He was appointed lecturer in 1993, senior lecturer in 2000. He is author and co-author of 60 publications and 5 book chapters. He was the secretary of the electrochemical group of the Royal Society of Chemistry, visiting professor in the University of São Paulo, working with Mauro Bertotti group that will be giving a lecture tomorrow. University of Bordeaux, National Polytechnic Institute of Grenoble, and University of Oldenburg. His research on microelectrode and scanning electrochemical microscopy has led him to deliver postgraduate courses overseas, here in Brazil too, and to present invited research seminars at UK and abroad. From his first year at the Southampton, he's begun involved in the Southampton Electrochemistry School, as I mentioned. It is important to highlight that because this school is very, very famous one, initially as demonstrated and now as a lecturer and in the main organizer. He has been teaching physical chemistry, in particular kinetics and electrochemistry at undergrad and postgrad levels for over 20 years. Thank you to be here, Guy, and it's a very honor to us to have you here. Thank you very much to be here, and the stage is yours to talk about us in the first part of the third to talk about modeling. Thank you very much, Guy. You only need to activate. Oh, you activated your mic. Thank you.
Thank you very much, Tiago, for the kind invitation to take part in your summer school. It's been a pleasure to be involved with your department over the years, and I have fond memories of being present in São Paulo to teach on previous summer schools. So I'm very happy to be part of this one again, even though it's online. I'm sharing my screen. I hope this is working. Can you confirm?
It's working. Is everything okay?
Yeah. Thank you very much. So hello, everyone. Good morning, good afternoon, wherever you are. So what I want to do with these 3 lectures on modeling is just to give you an idea of the techniques that we are using nowadays to analyze our experimental data, and to give you some idea of how this works and how we can put together some very simple models and simulate them with computers. So the topic, the syllabus that I want to cover involves a number of models, which I've listed here. I hope I will have time to go through most of those over the next 3 days. We're going to kick off with a very simple one, which is basically simulating the chronoamperometric response of a large electrode on the planar diffusion. And then we'll, with the background they've fully developed there, we're going to build the more and more complicated models, for example, with more complicated techniques, including more species. We're going to involve coupled chemical reactions and electron transfer kinetics. And then we're going to look at other situations, for example, a galvanostatic experiment for the charge of a battery. And then we're going to move to, in the third lecture, we're going to look at more complicated electrode geometries, such as the microdisc, but also we're going to consider how to simulate situations where we have more than just diffusion. So this will be a case where we have diffusion and convection in a channel flow cell. So this is just an overview of the cases that the examples I'm going to cover in this lecture. But with that, I hope to give you a flavor of 2 numerical techniques that are extensively used in electrochemistry to simulate our experiments. One is finite difference. So this is the one I'll be covering in great depth because it's a very easy one. Everybody can attempt that with a spreadsheet. For example, you can simulate over thermogram once you know how to exploit the equations. And then I will, in the last lecture, we'll move on to finite element methods because this is the one that is nowadays more used by researchers using a particular software called COMSOL multiphysics. So this is the syllabus, and the objectives of these lectures is twofold. First, I want you to understand, I want you to obviously understand the terminology which people use when talking about electrochemical simulations. But also I want you to understand the differences between simulation techniques. So we will only cover 2. I don't have enough time to cover more than that, but they are the most important ones, so that's enough. But I also want you to understand the limitations of the methods and the complexities of these methods. The other objective I want here is I'd like you to be able to assess how modeling is being used, for example, in the electrochemical literature. So being able to make a judgment about the models and how they've been implemented. That is very important. I also would like you to be able to, having attended these lectures, you should be able to select a particular technique for a particular electrochemical situation. And ideally, you should be able to simulate some basic electrochemical processes. So the one we're going to cover today, I can assure you, you can write your own code and you can simulate this problem in a spreadsheet, for example, or in simple code in Python or in BASIC, whatever programming language you want to use. But at the end, I will also show you how we can use commercial and open source electrochemical modeling software. And the one I will be developing the most here will be COMSOL multiphysics for more advanced problems, but I will talk about other electrochemical solvers which are available nowadays. So these are the objectives, and hopefully we'll manage to cover all these during these 3 lectures. So why should you get involved in modeling? Why bother, really? Well, essentially, it's because electrochemistry is an interfacial science, so we're looking at all sorts of processes at the interface, but also before and after the interface. So overall, we're dealing with rather complex situations. So we have the issue of mass transport, which determines how quickly the reactant reaches the electrode surface, but also how quickly the products move away. We will see that obviously the reactions involve many species. There will be different time scales and length scales. So this is really critical. I will show you in a few slides the different time scales and length scales that we need to take into account when modeling electrochemical problems. Of course, because we are dealing with chemistry, there are issues regarding thermodynamics and kinetics, and we need to be able to simulate both, sometimes together, sometimes separately. So we need to see how that can be implemented in the model. Of course, we're dealing with materials, with chemicals, and their properties will be very different. And of course, the electrical properties will be very different. So that will also be, that will need to be included in the model, sometimes, not always. The electron transfer, if we just focus on the interface, on the electrode solution interface, for example, the electron transfer can be extremely complicated. And in particular, because we can have adsorption. Susana was talking about electrocatalysis before, and she was talking about the strength of adsorption and desorption and how that impacts on the rate of your catalyst. So we need to account for that as a possibility in the models. Often we will neglect it if it's not necessary to account for it, but very often we need to implement it in the model. There are more complicated systems. For example, if you look at batteries, for example, you can have solid state processes, which will involve insertion, intercalation of some ions within the solid state matrix. And then, of course, there would be the reverse process, the extraction of the ions. We could be looking at, for example, if you are trying to model a fuel cell, you'll be looking at a three-phase boundary between the gas phase, the catalyst, and the electrolyte. So there may be situations where the model needs to account for transport and reaction at three-phase boundaries. So this is why we need to model, because although there are some analytical mathematical equations that we can use from the textbooks, for example, most of the time the real world problem is far more complicated. And although we're not going to combine all these problems at the same time, just the fact that we can, for example, combine mass transport with kinetics, you will see, is already very complicated and sometimes often beyond what can be done from a purely mathematical point of view. But the objective of the model is to simulate and predict what our electrochemical system is going to deliver. So we want to see the impact of key signals, for example, the current, the charge, the electropotential, the cell voltage, but also the impedance. If you're doing electrochemical impedance spectroscopy, we want to be able to understand that during the course of our electrochemical process, and we want to see how that varies with a number of experimental parameters. So there are many, as you can see, there are many reasons why you should consider modeling. But there is another one which I didn't put there, and for me it's very important. And this is how I got to modeling. It's trying to understand what's happening in your experiment. Modeling is a very powerful teaching tool because it forces you to ask questions. It forces you to query what is really happening in your electrochemical system. Why is the current having this particular value? Why is the current changing as a function of time? And by writing a model, you have to sit down and ask yourself many, many questions as to what should be included or not included. And I'm sorry about this noise. We're experiencing a thunderstorm in Southampton at the moment. That's just the rain hitting my windows. So I think what you need to remember is that modeling is extremely powerful to help you understand and what's happening in your electrochemical system, but also help you answer some simple questions. It forces you to think about what should be included, what can be neglected, what assumptions are required in your in order to understand your experiment. So I was talking earlier about length scales and time scales. So I've put this table together to give you a flavor of that we need to deal with in electrochemistry, but also the different time scales. So if we just start with the length, initially I'm looking right close to the electrode surface. So I'm looking at the structure of the double layer. So the first sort of length is the inner Helmholtz layer. So here we're looking at angstroms. At the outer Helmholtz layer, we're already at the nanometer scale. For the rest of the double layer, we are now encountering the diffuse layer, which, depending on the ionic strength of your electrolyte, could range from nanometers to millimeters. But then mass transport is involved. So we've got the diffusion layer, which, according to time scale, could be anywhere from nanometers to millimeters. If a reaction is involved in solution, then we will need to consider the reaction layer thickness, which could range, depending on the kinetics, from nanometers to millimeters. If mass transport by convection is involved, then we could have a boundary layer, which is typically of the order of micrometers. But then, as Gabriel will cover in his last lecture, when we start playing with tiny electrodes, such as microelectrodes and nanoelectrodes, we have to worry about the characteristic dimension of the electrode. And we could deal with electrodes ranging from nanometers to centimeters. So already you can see that as far as length are concerned in electrochemistry, we are dealing from a multi-scale problem, which will range from angstroms to centimeters. And from the point of view of modeling, this is very, very challenging. Now, if we consider the times involved in electrochemistry, it's equally challenging. If we start with the fastest of all the processes, which is the electron transfer process, we're looking at femtoseconds. In contrast, the nuclei are reorganizing, repositioning on the picosecond timescale. So already 3 orders of magnitude here in terms of times. To charge and discharge a double layer, you're now looking at microseconds to milliseconds. To perform an experiment such as a chronoamperogram, you'll be working typically from milliseconds onwards. But if we work with microelectrodes, we might be working from microseconds onwards. So again, the experimental timescale here could be very large. If we play with the sweep rate in voltammetry, we'll be changing the timescale of the experiment, again, from microseconds to milliseconds or minutes even. The diffusion layer has an associated diffusion time, or a species diffusing in our system has an associated diffusion time. So we need to take that time into account. This is probably one of the most important times that we need to be aware of with the characteristic time of our experiment. If we have a chemical reaction, we'll have a reaction time, so a half-life, for example. So we need to be aware of the half-life of the species involved in the couple chemical reactions. If we have a generation collection experiments, for example, as in rotating ring disk experiments, the travel time between the electrodes need to be accounted for. And then we also have other experimental parameters, such as the rotation rate in rotating disk experiment, or in AC impedance, we will have the frequency, which is another way of defining the time scale of our experiment. So there again, we have a very wide range of time scales that need to be considered. And of course, we can't model all of them, but we'll need to be aware of these, and we may need to ignore and make some assumption for other time scales. So when you're modeling, you need to be aware of these two issues, length and times, and very often they are linked. And we need to make decisions because the type of simulation technique that we will need to use will very much depend on the length scale and time scale that you're trying to model.
Sorry to interrupt you. We have a question here in this slide. Rona is requesting a theoretical information about the difference between the diffuse layer and the diffusion layer.
So the diffuse layer is essentially the length that is required in the electrolyte for the solution to recover the electroneutrality. So it's a region of electrolyte where you don't have an equal amount of positive and negative charges, because basically that part of the solution is still affected by the charges which are held on the electrode. So this is why I said that it depends on the electrolyte concentration. So if you have a very, very concentrated electrolyte, you will recover electroneutrality within a nanometer from your electrode surface. But if you have a very dilute electrolyte, the impact of the charge on the electrode will be felt very, very far away, and you might have to go to micrometers or tens of micrometers to recover the electroneutrality. So that's purely driven by electrostatics. So it's called the diffuse layer. In contrast, the diffusion layer is a very different beast. That is to do with how far species diffuse to and from the electrode when you are creating a change of concentration at the electrode surface. So for example, your electrode is consuming some species, this will induce a concentration profile, and with that concentration profile, there will be what we call a diffusion layer. So this is to do with the random walk of species in the electrolyte, and it will be observed as a concentration profile. So very, very different quantities there, but very good question.
Thank you, Guy. Rona is saying thank you in the chat too.
So with this slide, which I've picked up with this from this article, modeling techniques that we could consider for electrochemical simulations. So on the vertical axis, we've got the time scale of our experiments or problems. And then on the horizontal axis, we've got the length scale. So these are the two scales I was discussing before. Now, if we want to work at the femtosecond and picosecond, then we're going to be using quantum mechanics and DFT calculations, for example, to model electrochemical problems. If you move up the scales, both in times and lengths, you will see that you'll be using a different technique. This will be molecular dynamics. And then if we move up again, you could have, for example, kinetic Monte Carlo simulation. I've never used these because these three are, although quantum mechanics is increasingly used in electrochemistry through DFT, I have never seen these two being used very much in electrochemistry. There are a few simulations which involve the mesoscale. So this would be, for example, simulated with a technique called the lattice Boltzmann. But essentially, I'm not going to cover these because I want to focus on the continuum length scale. And essentially, I want to simulate, I want to show you what we can do with the transport equations and the modelers which are available, the commercial modelers and the open source modelers that are available nowadays. They all focus on the continuum length scale. And this is where I will be introducing finite difference and finite element methods. I'm aware that there are now some commercial DFT packages which begin to introduce some processes at solid liquid interfaces, but it's the very beginning. So all my 3 lectures concentrate on this region. And you can see from the form of the equations that we're going to be solving partial differential equations, essentially how the concentrations are going to change as a function of space and time. So this is a kind of recipe which will help you decide the steps that you need to take into account to build and construct a model and then implement the model in a particular software, for example. So the first part is to be very careful about what you include in your model and make sure that you don't, I will show you, we need to simplify as much as possible. So we make assumptions often. So you need to identify what is absolutely critical to go into your model. So mass transport is one of the problems that we need to consider most of the time. You want to simplify the geometry, and I will show you how we can do that when we look at complex electrode geometries. You want to then select what experiment you're going to do with your electrodes, and essentially you want to decide what is being controlled. Are you controlling the electrode potential or the current? In which case you will see that the mathematics that comes from that is very different. You then need to control the type of perturbation. Are you going to do a step, a sweep, a square wave, an AC voltage, or an AC current? So the electrode perturbation will also need to be implemented in the model. You then need to ask yourself whether that simulation can be simplified by working in the steady state, or do you really need to consider solving for a time-dependent problem and have the full transient simulation? You then need to ask yourself how many species need to be considered in the model. Very often you will see we can make some very simple assumptions and restrict the problem to just one species, essentially the reactant in the electrode reaction. Often, it's a purely thermodynamic problem. So do we need to include kinetics? Probably not. But sometimes we want to simulate the kinetics of the electron transfer process or the coupled chemical reaction. So ask yourself whether kinetics should be included, and in which case, where. You will see that the mathematical models are essentially made up of a few parts. The first one is the initial conditions. So you need to say what is in your system. So what is your bulk concentration? You need to define your cell essentially as a function at t equals 0. And then you need to define boundary conditions. And essentially we need to consider two boundary conditions. One is what happens on the electrode surface. And there could be several conditions, as you will see. But the other boundary to account for is what happens in the bulk. If you have semi-infinite linear diffusion, for example. If instead you have a battery, there is no bulk. You have two electrodes. So you need to consider what happens on one boundary and what happens on the other boundary. So essentially in a model, there must at least be two boundaries, but you will see when we go to complex geometries, there could be many, many boundaries involved in the simulation. You then set up the partial differential equations, PDEs, which essentially will describe the forms of mass transport and reactions involved in the electrolyte. And then you may, if required, you may modify these partial differential equations to account for any coupled chemical reaction. So I'll show you an example how we can do that. And then when you have set up your simulation, you really want to start with a very simple set of parameters. For example, if it's a voltammogram, you might want to start with a very low scan rate. You run your simulation, and then you validate your simulation by analyzing the data. So if it's a voltammogram, you might analyze the peak potential difference, you might analyze the peak currents, you might analyze the evolution of the peak current with the scan rate or the peak potential difference with the scan rate. So essentially you test your simulation according to some very simple conditions. And when you've got that sorted and validated, now you can start changing the parameters to include the conditions that you really want to study. So essentially, this is a step-by-step approach that is rather reliable, and it will help you proceed through your simulation. So let's now focus on what we need to include in our model. What is it we want to do? Well, an electrode process can be broken down into many steps. So here I've got, in step 0, I've got a preceding chemical reaction, which we will often ignore. And this is followed by mass transport, then reaction electron transfer at the electrode surface, then more mass transport, and then possibly a chemical reaction in the bulk as well. So 1 and 3 are controlled by migration, convection, and diffusion. You know that we can ignore migration very often. We can control convection often. So the one we're left with is diffusion. So most of our simulations in electrochemistry simply involve diffusion as the form of mass transport. In contrast, step 0, 2, and 4, because they are chemical processes, they may be reversible processes, kinetically controlled processes. So you may have to, this is where you need to account for thermodynamics or kinetics. 2 may be complicated. So the electron transfer process may involve adsorption or desorption. And that's another thing that needs to be taken into account. So now I'm focusing more and more on how to write a simulation, and we're going to build a simulation towards the end of this lecture. So we're going to start by writing the problem in what I call the real world problem. So it's in dimensional form. That means that you write everything with units. Your concentrations are in mole per centimeter cube. Your distance is in centimeters. Your time is in seconds, etc. You then, because we're going to work with computers, you want to discretize all the variables. And when you've discretized the variables, you want to discretize the equations that go along with that. Following this, you then need to pick up an algorithm, which will be a numerical technique. So we're going to cover 2, finite difference and finite element. And you want to construct an algorithm that will solve essentially the concentration profile, so how the concentration changing with space and time. You then analyze your simulation, and then you check whether it's been accurate, stable, whether your simulation is converging as you want, etc. So the 3 steps here, I will show you how we can build our own models. But you can find digital simulators for electrochemical problems. One is called DigiSim, the other one is called DigiElk. These 2 are commercially available. Soft Potato is an open source software that was created by one of my students, and this is available to do simulations of voltammetry or pyrometry. Then there's Console Multiphysics, which is commercial software. And then there is FreeFEM, which is an open source version of finite element, which allows you to simulate all sorts of things as well. So we now need to move deeper into the way to create a simulation. You will see I'll be often talking about dimensionless problems. And the reason we do that is to simplify the simulations. Essentially, when you have so many variables, like the number of electrons, the diffusion coefficients, the area of the electrode, the concentrations, there are many parameters that are lumped together into a quantity, and there's no need to repeat the simulation many times. The mathematics can be shrunk to one basic dependence. So often we prefer to convert all the equations in the variable from their dimensional form to a dimensionless form. That means we try to normalize all the quantities to remove the units. And the rest is all the same. These are all the same steps as before. But at the end, when you have simulated, what you end up with is what we call a working curve. And a working curve, for example, could be normalized current against normalized time scale. And it's very powerful because you are summarizing a whole range of parameters into very well-defined quantities, and you simplify the mathematics tremendously. Sometimes we don't bother. We just go straight into dimensional simulations. But when you start from scratch, it's very useful to work with dimensionless forms because it reveals what actually determines the response of your system when you lump together the parameters. I'll show you some examples. So I hope that will become clear later on. So essentially, this is what we try to tackle in electrochemistry. So I'm now focusing on the electrochemical problem, but I'm now including the variables and the quantities that we need to solve. So we've got our mass transport, and this is going to be represented by partial differential equations, which are essentially fixed second law of diffusion. We have boundaries. So one boundary is the electrode surface. So this is going to be called x equals 0. And then we have another boundary, which in this case is the bulk of the solution. So this is x equals infinity. And then we need to set up the problem. So this is called the initial condition. So at t equals 0, you define what you have in the solution. So for example, I've got some reduced form in the bulk of my solution, but no oxidized form. The reduced form is going to travel by diffusion, it's going to be oxidized. So I'm going to create the oxidized form. So there will be mass transport of the oxidized form because that's the product of the reaction. The important boundary is the electrode. So at x equals 0, I need to say what's happening here. Well, in this example, in this lecture, I'm going to make a potential step from a value where the reaction is nothing's running to a value where the reaction is running as hard as it can. And that means I'm going to drive the surface concentration of my reactant to 0. The other constraint I have is that the flux of R must be equal in opposite to the flux of O. So already you can see that on the boundary, I have two constraints. One, which fixes the concentration, and one which relates the two fluxes. So here we have to account for gradients of species, concentration gradients. And here we impose a concentration. This will come back many, many times. As I make the model more and more complicated, I will be changing this boundary. A lot of the rest will remain the same. The initial condition will never change. The partial differential equations will remain the same. The bulk condition will remain the same. But as I change the nature of my electrochemical experiment or the electrochemical problem, very often I'll just be working on this constraint, and you will see how it changes the response of the system. The other thing I want to do on this electrode is to calculate the current. So the way to relate the current to the flux of reactant is simply to write it like this. You lump together the constants. We like to keep the diffusion coefficient on this side because this is the flux. So that's what we want to simulate essentially, is we want to solve these equations with taking into account these initial conditions and boundary conditions. So how can we solve these equations? Well, if you're a very good mathematician, you could do this with the Laplace transform. For the problem I described earlier on the previous slide, it's possible, but it will take you pages and pages and pages of mathematics, really. It's possible, but only for limited cases. As soon as you move to complicated electrogeometries, it becomes very, very difficult, and there are no closed form analytical solutions. So another approach is the numerical simulation, and I will show you finite difference and finite element methods. But there are other methods. Random walk, network method, which is an electrical network approach, also boundary element methods, but I won't talk about those. The numerical approach is powerful because it allows you to simulate some real world problems, even though they may not be in the mathematical solution. So you need to define your solution simulation domain. You need to decide whether it's a 1D, 2D, or 2D axisymmetric, maybe 3D simulation domain. You need to discretize the domain. So we're going to talk about meshing. This is particularly important when we do finite element simulations. We need to initialize the concentrations. So basically say to the simulation, this is what we have in our electrochemical cell. We solve the partial differential equations on the mesh, taking into account the boundary conditions. And then when we've solved the concentrations, we then calculate the current. We plot the concentration profiles. We might calculate the potential if it's a galvanostatic experiment, or we might calculate the impedance. So essentially, this is how it works. So this is my first example, and I will build it up slowly. Later on, when I take more complicated example, I will go a little bit faster. So I call it the Cottrell equation, because this is the equation that describes the current on the diffusion control, so semi-infinite linear diffusion. So it describes the current as a function of time when you step the potential from one particular value, EI, when there's no reaction running. You see the current is 0 here. When you step it to a value EF, where if we had a rotating disk electrode, you would see the voltammogram as this shape. So I'm driving the reaction as hard as I can to make sure that the surface concentration of the reactant is equal to 0 on the electrode. So I want to simulate the current when I jump from E1 or EI to EF. Now, I know this because there is a theoretical expression for that. So this is purely an example for teaching you how to do this. I am expecting, and this is a working curve, you see it's a dimensionless current and dimensionless time. I'm expecting the current will drop as a function of time according to 1 over the square root of time. So this is my, this is the shape of the current transient which I want to simulate. So I will show you how we can do that very simply. And this is the example that you could solve. You could put yourself, you could write yourself in a spreadsheet. It works very well. So this is the problem in dimensional form. So I have my reactant R and my product O, and these are the partial differential equations for mass transport by planar diffusion. So these are the second fixed second law of diffusion for these two species. This is my initial condition. So I'm imposing the bulk concentration for the reactant and 0 for the product. There is no product in the cell to start with. This x equals 0 is the electrode surface. So I'm imposing 0 surface concentration of the reactant. I'm saying that the flux of O and R are equal in opposite. And then this is is not a constraint, this is the equation that I'll be using to calculate the current. Far away in the bulk at x equals infinity, I will be recovering the initial condition because essentially the reaction never reaches that far. So the bulk will not be affected by the reaction. Already, if you think forward, you will see that we need to address a particular question. Can I really account for infinity in my cell? How can I implement infinity in my simulation? So this is something we'll need to address, and this will come to later on. So I'm going to use PDEs for partial differential equations, IC for initial conditions, and BC for boundary conditions. Essentially, when we change the electrochemical experiment, for example, when we implement voltammetry, or if we do AC impedance, for example, this is the part of the problem that will need to be modified to account for the perturbation that we are imposing on the system. So this is in dimensional form, and you notice that all my variables are in lowercase. I'm now going to show you how we can simplify this. So to simplify, you need to define dimensionless variables. So we have essentially 3 variables. We have concentration, distance, and time. So to make the concentrations dimensionless, it's very simple. You decide to normalize all your concentrations with respect to one value. So very often we take the bulk concentration of the reactant. So now you notice that these are lower cases, but this is capital case. So my capital case correspond to the dimensionless concentrations, dimensionless distance, and dimensionless time. So this will be the dimensionless concentration of reactant and the dimensionless concentration of the product. To make the distance dimensionless, I need to divide by a characteristic length. So very often we take a characteristic distance, which in this case is the diffusion layer. The diffusion layer is defined as the square root of diffusion coefficient times a particular time, tau. Tau could be the duration of my experiment, for example, or it could be the duration of one sweep in a voltammogram. So it's a choice. This is something you define as your characteristic time. But for that characteristic time, there will be a characteristic distance, and this is the value I'm going to use to normalize the distance. For the time, I'll be using tau, this characteristic time, to normalize my time scale, to make a dimensionless time. Now, when I implement these three expressions into the current, I can define a dimensionless current, which is basically a gradient of dimensionless concentration. And depending on how I express my dimensionless quantities, I will end up with different expressions for the dimensionless current, but at the end of the day, they mean the same. It's just that there's a relationship between delta and the square root of tau and the diffusion coefficient, that's all. So this is a very simple way of simplifying the problem and generating a working curve at the end. So this is the same problem, but now rewritten in terms of dimensionless form. So I've got my dimensionless mass transport equations, so PDEs. You will see that because I've divided by, if I go back here, let me go back one more. You see, we have dr and do. So when we normalize, we'll end up with a new quantity, which is a normalized diffusion coefficient, which is what we have here. So this is a quantity that we will need to remember in the future. So normalized time, normalized initial conditions. These are the normalized boundary conditions, normalized current, normalized bulk boundary condition. Okay, so it's exactly the same problem, but it's been rewritten in simpler terms, if you want. I'm going to make another simplification because to teach, it's very useful to do that. But when you are developing a model, it's also useful to start from the simplest problem possible. So recognizing that very often the oxidized and reduced form of the species involved in the reaction are not that different in size, they will probably end up having a very similar diffusion coefficient. So if we make that assumption, we can show that throughout the solution, anywhere in the solution, the sum of the oxidized and reduced form concentrations is equal to the starting material. So that means we now have a relationship between these two species, and therefore I can express the oxidized form, so the product, in terms of the reactant. And so now, instead of working with two species, I can simplify my problem and do everything in terms of one species. So I will simplify the simulation quite a lot by removing one species in the problem and just simulate the concentrations profile for the reduced form. So now we are at the point where we need to think about implementation in the computer, and we need to discretize. So we have essentially three quantities that need to be discretized: the concentration, the distance, and the time, because we want to be able to compute these in the computer. So I'm going to rewrite them. Instead of writing c as a function of x and t, I'm going to write c as a function of I and k, where I is an index for location and k is an index for time. Essentially, it's just a computer representation of the concentration as a function of space and time. So whereas that would be a continuous representation, this would be a discrete representation suitable for a computer program. So k will be my index for time and for time increments, delta t. At k equals 0, we've got the beginning of the experiment. At k equals k max, we've got the end of the experiment. And I is my index, which will allow me to work my way through the simulation, the cell, in terms of distance away from the electrode with increment delta x. I equals 0 is the electrode surface, and I equals I max is the far end of the solution that I want to consider. So if we were to do this by hand, this is how it would work. On the vertical axis, I've got my concentration. On the horizontal axis, I've got the distance. Far away, I'm in the bulk. You see, this corresponds to I max. Close to the electrode at I equals 0, I've got the electrode on the left-hand side. At K equals 0, which is the black line, my concentration is flat. This is the concentration of the reactant. So this is the initial condition. At K equals 1 in yellow, I have now started the simulation. So I've stepped the surface concentration to 0 because that's my boundary condition. And now I've created a concentration profile. So what's going to happen is the partial differential equation, which models the diffusion, is going to draw my concentration profile more and more to the right. And we can see that evolution with time. So K equals 1 is the yellow, K equals orange, K equals 2 is in orange. So this point here has now evolved to that one, but this one hasn't been touched yet. At K equals 3, the first point has now evolved to this new value. This one has evolved to that one. This one hasn't been touched. K equals 4. This one has changed to this one to that. And then at 3 delta x, we now have evolved to this new value of concentration. But this one hasn't been changed. So you can see that we could do that schematically. And this is what the simulation will be doing. It's going to adjust these concentration values according to space, that means this way, and according to time, that means that way. You can see that what nature is trying to do with the diffusion is trying to smooth out the concentration profile and even out the concentration profile across the whole cell. So there's another way of looking at this, which I find very useful, and it's a matrix representation. So what I have done here now is I've got I, my space index on the horizontal axis. So here we are in the bulk, here we are on the electrode surface, and I'm interested in a concentration CIK, so at position I. There will be I minus 1, which is the concentration just before on the left, and I plus 1, which is the concentration just after on the right. But on the vertical axis, I've got K. So this is my time index. So I want to compute the concentration at CIK. So this is what I call the present. But I will have information from the past. So all the values at CIK minus 1. Or I will also have to work out concentrations in the future, which is K plus 1. So what we need to do is come up with a way of completing this matrix by zipping through from left to right and bottom to top and working out all the values for the concentration of interest. And so essentially the algorithm I will show you is the simplest algorithm to do that. But we have to mathematically compute the partial differential equation. So we need to approximate them and discretize them. So the way we do that is by using a ratio of finite differences. So we simulate the derivatives by estimating them by calculating ratios of differences. And that's what the technique is called finite difference. So if you look at this graph, so we've got y is a function of x. Imagine I want to calculate the derivative of y at this position x here. I can see 3 ways of doing it. I can take the forward derivative, which is the pink line, or I can take the backward derivative, the backward gradient, which is the green line, or I can take the gradient across the forward and back, and this is the blue line. So if you write this in terms of equations, you will be approximating your derivative at x according to the pink gradient, which is yi plus 1 minus yi divided by xi plus 1 minus xi. This is called forward difference because we're going forward of where we are. You could do the opposite, which is the backward difference. So now the green expression is the gradient for the green line. Or you could do the central difference, which is going across from forward to back along the blue line. And now you can see the indices is I plus 1, I minus 1, I plus 1, I minus 1. So these are the approximation that we're going to make to calculate the derivatives and essentially use those to solve the fixed second law of diffusion. So if we now look, yeah.
Can I interrupt you? Sorry. We have two questions here in the chat. Oh no, now we have more. Oh, there is one first question that the relation CO and CR both is the question about the CO and CR. Does it come from the assumption of the diffusion of the oxidation species equal to the diffusion of the reduced species, or it rises due to the reaction, the stoichiometric reaction? Yes, these ones.
Yeah, you could put the stoichiometry in there if you want, but most of the time we just assume 1-to-1. But essentially, it's the conversion of one of the reactant into the product, which has to be equal to the starting material. So yes, the stoichiometry comes into play. But the other thing that comes into play is the diffusion coefficient. So it's a bit more complicated than that, because if you don't make this assumption, you can't write this very simple relationship. The general expression involves the diffusion coefficients. If DON is not equal to DR, you wouldn't be able to write this. You would have to include diffusion coefficients at all locations. So yes, it involves the stoichiometry, but it also is only possible because of this assumption. Otherwise, the expression is much more complicated.
The other one, it's about the how the participant could know the value of the distance and the time max values. Probably how we can add these values in the simulations.
You mean Kmax and Imax?
I think that is not the Kmax. Seems that the value of the distance and the time max. Where is the time max?
The time, I'm not sure if I can see.
I think that because the only question that we have here in the, let me check if they will reply something different. No, it's only this. It's about to know how the value of the distance. I think that because they are thinking how we can know the distance, so the diffusion distance probably could be, and the time to achieve the max current.
Maybe this comes to that.
Yes,
delta.
Yeah.
So there are many ways of doing that. Imagine that I do a potential step, and I want to acquire the current for 1 minute. Then I would put tau equals 60 seconds, and that would allow me to estimate the diffusion layer thickness for 60 seconds, and I would use that to normalize my my distance. Okay. If I do a voltammogram, for example, and I'm sweeping at a particular scan rate, then this will determine the time scale of my experiment. I will be able to calculate a value of tau based on my scan rate and the potential limits, and I can use the apparent diffusion layer thickness delta for that particular time scale. It's a choice. You could choose any value you want, but often in electrochemistry, we like to choose values of time scales and distances which are related to the experiment. So later on, I think tomorrow, we're going to see an experiment or simulation where I simulate the charge of a battery. So there, I am not going to choose the time scale. I'm going to choose the distance, and the distance will be the characteristic length of my electrode in which I do the insertion. So instead of defining, you see the way I do it here, I start by choosing a time, and that determines the distance. When I will simulate the charge of a battery, I will do the opposite. I will choose a length, and that will determine a time in the same, but using this expression in the other way around. So because time and distance are always linked in electrochemistry, you either decide how long it takes, what is the time scale of your experiment, and that relates automatically to the distance, or you decide, you select the characteristic distance of your experiment, and this determines the time. For example, when we work with microdisc electrodes, we do it that way as well. We select the characteristic length, which would be the radius of the microdisc, and this defines a characteristic time. So you have two ways of doing it. You either choose your characteristic time, and that determines the characteristic length, or you select you choose your characteristic length, and that determines the characteristic time. But either way, they are linked. So it's a matter of choice.
Thank you, Guy.
So I think I was here. Yeah, so we've just finished discussing the approximations for the derivatives. So now I want to show you how we implement them. So this is the fixed second law of diffusion in terms of dimensionless quantities. So they look very clean, very simple. On the left-hand side, so LHS means left-hand side, I've got dc dt at location X. So I'm going to approximate this by a forward difference in time. K is the present, K plus 1 is the future. I is the location of interest. So because X is constant, I is the same for both concentration. But because I'm looking for a derivative with respect to time, I've now got to change K and K plus 1. Now for the right-hand side, RHS is the right-hand side, we've got a double derivative. So it's a second order. So I can rewrite it as dc dx differentiated with respect to X. But this is constant time. So the K values here will be the same, but what is going to change is the I values because we're doing a derivative with respect to X. So now, because I have a double derivative, we have to use a combination of differences. So I'm going to use a forward difference in space, so forward I plus 1 I, and then here a backward difference in space. So I've got a gradient of concentration here and then another gradient of concentration. This one is a forward difference, this one is a backward difference. And then to calculate the double derivative, I take a central difference. So we've got forward difference, backward difference, central difference. And that allows us to come up with this very simple relationship where we've got K, 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 I plus 1, I minus 1. So this will be the discretized right-hand side expression for my fixed second law of diffusion. And for the left-hand side, we've got this one. So put together, this is what we have in the continuous form, and this is what we have in the discrete form. The left-hand side in terms of K, because it's a time derivative, the right-hand side in terms of I, because it's a space derivative. So on the left, I is constant, on the right, K is constant. So this is our discrete representation. And what we need to do now is to solve for what we don't know. And the only thing we don't know, if you look at this, K, 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 this is all the present. We know the present. The only thing we don't know is the future. So there is one equation with one unknown, and this is the unknown. So one equation with one unknown, I can solve it and come up with an estimate of Ci K plus 1. So I can rearrange and put the unknown on the left and the knowns on the right. I can rearrange further. And what I do here is regroup the terms. So I've got delta T over delta X squared. Now this is an important quantity. We call it lambda. delta T over delta X squared. If you express it in terms of real world quantities, so with unit, it's D, diffusion coefficient, delta T now with seconds, and delta X squared centimeters. So centimeter squared per second times second is equal to centimeter squared divided by centimeter squared. That's a dimensionless quantity. So lambda is dimensionless. And because it's a kind of dimensionless diffusion coefficient, we give it that name. That's how it's called in the literature. So if I regroup these two terms into lambda, and then I've got CIK here and CIK there, I can regroup. So I've got an expression for the unknown in terms of three concentrations at K, 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 but I plus 1, I minus 1. So you can see that we can calculate the new concentration at I in the future using these three concentrations in the present. It's called explicit finite difference. So finite difference because we're calculating a ratio of differences, but explicit because we're using the present to calculate the future. I will show you some other examples where I use the past to calculate the present. So instead of having K plus 1, I've got K, and then instead of having K, I've got K minus 1. But it doesn't matter. Basically, what it means is you are taking the values that you know to calculate the values that you don't know at the next step. So there is one constraint that we need to be aware of, because this scheme will only work if the change you make to the concentration I between the current time and the new one, this change has to be small compared to these values, and it's got to be less than half of those, which implies, if you work it out, that lambda must be less than half. If you make lambda bigger than half, you will find that, and you can try that if you put this in a spreadsheet, for example, what you will see is that the simulation will start working, and then the concentrations will start to oscillate, and then the concentration will become increasingly stupid and eventually become negative. And this is what we call instability, and your system, instead of converging towards the correct solution, it's diverging away from the solution, and you end up with negative concentrations. So this is a particular quirk of this numerical scheme, but every numerical scheme has its own constraint, and these constraints will determine how quickly it converges, whether it is stable or poorly stable. So you need, when you choose a numerical scheme, you need to be aware of these constraints. So let's look at the whole problem again in this matrix representation. So I've got time on the vertical axis and I've got the distance on the horizontal axis. And what I've done now is to represent with colors what I know, and the blue region in the middle is what I don't know. So what I know from the start is the bulk solution, because this is the boundary condition in the bulk, and I know that those concentrations, they're not changing. I also know this region here, the initial condition. So all the values along that line, I know them because that's what I put in my solution at t equals 0. And the other thing I know is what's happening on the electrode surface. I may not know the surface concentration. I may not know the flux, but what I know is a relationship between all the quantities. So we either know the concentration, or we know the flux, or we know a linear combination of concentration and flux. So in most electrochemical simulations, what we end up doing is imposing these conditions all around, and then we choose a numerical scheme. So this is the explicit finite difference, which allows us to zip through from the bottom to the right and up all the way. We zip through until we completely calculate the matrix. And at that point, we've got all the concentration profiles and we can do some calculations. So the way it works is that I'm going to calculate the pink value here, knowing these three values. When I've done this, I can move to this one and I can calculate this one, knowing this one, and this one, and so on and so on. That's what I mean by zipping through. And there are many mathematical ways of doing that, but this is a very simple one. And it's not very efficient, but it's very easy to understand and it's very easy to implement. So it's a good one to start with. So how do we get the current? Because of course we want to get some numbers out of our simulation. Well, to get the current, we are going to differentiate the concentration profile at the electrode surface. And because it's been discretized, I just need to take the difference between the first concentration in solution, subtract the concentration on the electrode surface, divide by the distance, and that's going to give me the gradient, which will be the dimensionless current. So if I do that for every iterations in time, I will have the current for all the iterations in time. So the calculation of the current is very simple. Calculating the potential is a little bit more tricky, as we'll see tomorrow. So this is how it works. So we've done it manually. This is actually from a spreadsheet calculation. So you can easily do that. So K equals, so we've got our concentrations on the vertical axis. We've got our space index on the horizontal axis. So that's distance away from the electrode. At K equals 0, we've got the blue line. And then K equals 1 in pink, K equals 2 in yellow, then 3 and 4. And you can see that as the algorithm is iterating through time, that we can see the evolution of the concentration profile and we can see the buildup of that diffusion layer. This is now over a long period of time. And I've gone up to K equals 20. And what I want to show you here is that when you look at the shape of the concentration profile, it's quite jagged at the beginning. But as you iterate longer and longer, you find that the concentration profile looks rather smooth. So for this pale green here, for 10 iterations already, my concentration profile is very smooth. That means that the numerical scheme took about 10 iterations to converge. And by conversions, here I'm just looking at the shape of the concentration profile. Now, from the analytical solution, I know this is the complementary error function, and I know it's got this sort of rounded shape. So I can tell that my scheme here only took about 10 iterations to compute the correct concentration profile. So these are all.
Sorry, to interrupt you. We have a question
on.
here in the chat, and the question is about the constraint lambda lower than 0.5. It is a result of the FD discretization being a non-conservative method. It means if I use the infinite volume instead of FD, should this constraint be restricted to maintain it?
The constraint comes from this here. Okay, you are approximating derivatives with differences. So you're making growth assumptions here, and it's not. It's a very gross way of estimating a derivative. And for this scheme to work, you need to make sure that the changes between one step and the next are not too big. So you need to make sure that what you're doing on the left isn't too big. Otherwise, you're making steps that are too large to be valid. So if you think about this new value of concentration as being a kind of average between 3 values that preceded it, you can see that if lambda is too large, then you will end up with making big changes which are not sufficiently accurate to approximate the derivative. Now, there are other numerical schemes which do not have that constraint. So, for example, there is a scheme called the Crank-Nicolson scheme, which is much more complicated to implement, but much more efficient, and in particular allows you to have to not have the constraint on the value of lambda. There are other schemes, for example, if you solve this problem using the Runge-Kutta numerical scheme, again, there are no limits. So this particular constraint is inherent to that numerical scheme. If you were to choose another numerical scheme, you would be able to, there would be other constraints, but not on the value of lambda. And if you do finite element, there will be it will be a completely different way of solving these partial differential equations, and you won't have that constraint. So this one is totally inherent to this explicit finite difference scheme.
Thank you, Guy.
Where was I? Current concentration. Right. Okay. These are the concentration profiles, and now I want to show you the result in terms of the current. So this is what you get when you plot the simulated current as a function of the iterations. So of course, the first iteration you jump, because of course at t equals 0, the current there was no reaction. So you jump, so it's a big step. And then you can see that the current is oscillating a little bit, but essentially is dropping. And if you wanted to plot that as 1 over the square root of k, you would find that the current is proportional to 1 over the square root of k. This is what I call a working curve, you see, because this simulated current, which shows psi in my previous slide, and k, which is equivalent to the dimensionless time, this is independent of n, independent of d, independent of the bulk concentration or the area of the electrode. This is the curve that defines this problem, whatever the other values you put in your system. In the past, it was efficient to do it in dimensionless form and to work with working curves because we didn't have enough computer power. Nowadays, most simulators for electrochemical problems do everything in dimensional quantities because it's so fast to simulate that we don't have to worry about computer power. And they will ask you to enter your concentrations in real world unit. They will ask you to enter your area of electrode in centimeters square, and the simulation will be done in real world units, in proper unit. But I think you will benefit to work with dimensionless quantities to create working curves because you will learn about the key relationships between your quantities and the dependence of, in this case, the current on time. But for a voltammogram, it would be dependence of the current on the scan rate, for example. So in this slide, I want to show you how the scheme was converging. What I've done here is to plot the simulated current with respect to the theoretical current. I know the theoretical current because it's the Cottrell equation. You could derive it by solving the PDEs using the Laplace transform. But here, this is how this ratio changes. So you see, at the first iteration, we are 20% away, and then we drop to just over 5%. And then by the second, we're under 5%, and very quickly, we are well within 1%. And this is where you can see that within 10 iterations, the scheme is already within 1% of the theoretical value. So although it's not a very efficient scheme, it's actually pretty reasonable already, and it's very simple to implement. So I like the explicit finite difference scheme because I can write this simulation in about 20 lines of code in, say, Python or MATLAB or C or whatever computer language you use. If you want to do the same thing with the mathematical approach and do the Laplace transform, now you're looking about 10, 15 pages of integrals and it's doable, but it's really, really painful. Whereas writing the code, it's fairly straightforward. So I think, yeah, I need to give you a little bit more information about some of the parameters. How would you choose Kmax? So the Kmax is the total number of iterations to consider. In practice, I prefer choosing Kmax and working out everything else from that value. So I will say, for example, right, I'm going to put 10,000 iterations or 1,000 iterations or 100, depends what I'm simulating, okay? So the greater the Kmax, the smaller the delta T will be. But remember, we are making approximations, so the smaller the delta T, the smaller the delta X, and therefore the better we are at estimating the differentials in the PDE. So essentially, the resolution of the simulation, both in terms of space and time, gets better and better as you increase Kmax. Of course, it's going to take a lot more time to run if you make Kmax very large, and it will take a lot of computer space in the form of arrays of concentrations, and it will take a lot of memory. But nowadays, this is not an issue. It used to be an issue, but not anymore. What about the other parameter, Imax? Now, Imax will determine how far your diffusion affects the concentration profile. So how far should you go in solution? It turns out that we know roughly how the diffusion layer scales with time. So we know that the relationship between time and distance through this very simple relationship. So from Kmax, I can work out a relationship that's going to allow me to estimate Imax. And this is the way we do it. From the concentration profiles, we can work out that if you go to 6 square root of dimensionless time, you have gone beyond the diffusion layer thickness, and you have now reached the bulk concentration, which is not affected by the diffusion process. So at each iteration, time iteration k, there is no reason to compute the concentration profile beyond 6 square root of k dt, because beyond that, there's no change in the concentration. So you can work through the expressions, and you can show that the value of Imax is actually determined by the value of Kmax, which is, it's logical. I told you right at the beginning that time and distance are linked. So it's linked through this square root of time dependence. So if you choose Kmax, this determines Imax. And it basically says there's no need to simulate beyond that. And so you can use Kmax to determine how big your concentration arrays should be. So Imax will be the maximum array index for your concentration. So the algorithm looks like this. I didn't write it as code, I just wrote it as instructions. You can put that in any language you want. So you choose lambda. So I would suggest you choose it at 0.45. You can't make it 0.5. It's got to be less than 0.5. So make it as close as possible, but not equal. So 0.45 is a good number. You choose Kmax. You calculate these quantities. You then define the size of your concentration arrays, both in terms of I and K. You set the initial conditions. So yeah, that means you impose the value of the concentration at K equals 0, but everywhere. And then you have 2 loops. You have a loop for time, which is the K loop, and you have a loop for I, which is the space loop. So this is the zipping mechanism I was telling you about. In the loop for time, you set the electrode boundary condition. You set the boundary condition in the bulk. You then start the space iteration, where you calculate the new value of concentration, knowing the other 3 from the time before. You then calculate the current. So this is the explicit finite difference algorithm, if you want. You calculate the current from the gradient at the electrode, you complete the space loop, you complete the time loop, and you finish the simulation. This 20 lines at the most, that's all it takes to simulate this problem. And the way it's implemented, you can do this on a spreadsheet. It's very easy. So in summary for this lecture, these are the steps that I recommend to put together a simulation. You need to really understand your electrochemical process. You need to ask a lot of questions. You need to establish some simplifications and assumptions, because there's no need to you can eliminate a lot of aspects of the problem. Once you have done that, you can establish your mathematical model. You can make it dimensionless if you want. It's optional. At the beginning, I recommend that, but if you don't want to, you can bypass this part. You then need to discretize both concentration, time, and distance. You need to discretize the equations. This will give you a numerical scheme. So the one we've used here is the explicit finite difference, but if you are knowledgeable in numerical techniques, you can find other schemes. When you've done that, you solve to produce the concentration profiles, and from that you get the current. So essentially, this is the pathway that you need to follow to run a simulation. Now, if you're using a simulator, you still need to come up with your problem. I would still recommend that you make simplifications. You could do dimensionless. That depends on the modeler. The discretization will be done for you. The numerical scheme will have been selected for you. So a lot of these steps will be included in the solver. And what you need to do is either output the concentrations or, for example, output the current directly. So I think this is the end of this lecture. In my last slide, I've just given you a list of books which I recommend for going deeper into this area. Dieter Britz has written a wonderful set of books on digital simulation in electrochemistry. I strongly recommend those. If you want to go and look at these others, they all talk about simulation. They all have some chapters on simulations as well, if you want. But the books by Britz are definitely well worth having a look. And thank you very much for listening. I think this is the end. Yeah.
Thank you, Guy, for the amazing presentation. Every time that I listen to you talking about this, I learned something new. There is a lot of congratulations on the chat, saying that you gave a new look for the people see the equations and another approximations, and it's good to see you that you open the mind of the participants here. Bridget say really interesting talk, and everyone here in the chat is congratulating you for the talk. We will have Guy for more 2 days, and this is amazing presentations, and it's very good to see you here, Guy. Thank you very much. There's any other question here? Only this. Oh, there is one new. Oh, there is a question here now, and I will check. In case of absence of the analytical and experimental data, what could be a good, acceptable way to validate the simulation results? So
this is where I suggested that you should use, you should start from a simple set of input parameters. So imagine that you want to simulate a voltammogram, cyclic voltammogram, and you want to push the boundaries. You want to go really, really fast. So, for example, I mean, the world record, as far as I know, is 4.7 million volts per second for voltammetry at microelectrodes. Now, if you want to simulate that sort of speed, that probably will be challenging your numerical scheme or your simulator. So to validate the problem in the first place, what I would do is I would start with very low sweep rate and make sure that the voltammogram that's coming out is reasonable. And then I would increase the sweep rate. Now, if you are writing a simulator for voltammetry from scratch, and you want to check that your voltammogram is simulated voltammogram is okay, what you can do is, for voltammetry, we don't have analytical solution. If you look at the textbooks, there is no analytical solution that describes the shape of the current as a function of potential for a planar electrode. So even for the simplest voltammogram, we don't have the mathematics for it. But what we do is we have, for example, the peak potential difference. We know that if it's planar diffusion, it should be 59/n millivolt. It should be independent of the scan rate. We know that the peak currents are going to scale with the square root of the scan rate. So what you can do is you can select a handful of characteristic criteria, and you can validate your simulation by running the simulation for a number of parameters and checking if your simulation obeys the criteria that are known for this particular problem. And if you find that your simulation is not capable of obeying these criteria, then that means there's a problem with your numerical scheme or the way you have set it up.
We have a new one here.
Thanks.
Give you thanks, and I would like to ask about the performance of the EDF algorithm. Can it be benefit from a high degree of parallelization? It seems to the initial concentration and constant depend on the previous term would prevent it.
You can use parallel algorithms, but to be honest, that particular numerical scheme is not the one that I would try to optimize. You will see we can do far better with finite element, or we can. There are other schemes which are much better. For example, the Cronk-Nicholson scheme is very good. The Runge-Kutta scheme is also very good. So the explicit finite difference scheme, I use it because it's a very good teaching tool to introduce the concept. It's not the most, it's not the best numerical scheme, but it's a scheme that everybody, you don't have to be a mathematician. You just need to understand plus, minus, and division, basically. And obviously a little bit of electrochemistry, but it's a scheme that everybody can start with. And it's accessible, and it will help you understand a lot. When you've got to that stage, then if you want to optimize and get a better simulation, then forget about explicit finite difference and move to Cronk-Nicholson or alternating direction implicit or Runge-Kutta, or there are many schemes. In fact, if you have access to a software like MATLAB, for example, or Mathematica, they have built-in libraries of numerical schemes where they have already optimized the solvers, and you don't, you just set up the problem, set up the boundary conditions, the initial conditions, and then cast the problem in the format that is required by the solver, and then you just let the solver do the number crunching for you. This is what I do nowadays. If I want to write my own simulation, I will go into MATLAB and I will try and use one of the MATLAB numerical routines, because these guys, that's their job. They're optimizing these things for us. So I'm not a mathematician. I'm just an electrochemist. So I try and rely on these guys to provide me with the tools that will allow me to crunch the numbers. But I have to set up the problem in a proper way in the first place. And that's where I think this approach is helpful, because whether you use EFD or something else, at the end of the day, you still have to solve the partial differential equation. You still have to set up an initial condition and have proper boundary conditions which are coherent with the electrochemical problem. Afterwards, what you do in between, it's almost like a bit of a black box. However, you will see that when you use a commercial simulator, for example, DGELC, which is a very good one, there are some parameters in there which are very relevant. So if I go back to this term here, you see this 6 kdt or 6k max. This expression comes in the DGL. You've got the default parameters, but then you can tweak some parameters, and this expression comes in there. So you will see that even with the commercial simulators, it's helpful to have this sort of information, because the commercial electrochemical simulators are still referring to this sort of ideas. I hope I've answered the questions.
Yes,
okay.
yes. We have a lot of other people in the chat writing. Yes, Lorenzo said that you answered the question. And we have a lot of people saying thank you, Gui. It's a very clear answer and presentation. Thank you very much. Again, I will follow the people in the chat saying thank you to you, Gui. And it's a pleasure to have you here. And it will be a pleasure to have you in the next days. Thank you very much all for the audience here today. And I would like to thank you, all the participants. We have a lot of questions during the days and good questions. Thank you very much for all here inside of the Zoom meeting room. And I would like to thank you very much. Gui, thank you again. And today we will finish, and tomorrow at the same time, we will continue our discussion, our electrochemical week discussion. Thank you again all. And thank you, Gui, again to help us with the simulations. Bye-bye, people.
Thank you, everyone. Bye.